Good morning, good afternoon, good evening to all of our Geek Speak attendees. We're happy to be with you again this fine Thursday towards the end of October. Hopefully, wherever you're coming to us from, the weather is sunny and bright as it is on the East Coast here of the US. As always, my name is Matt Burns, Technical Marketing Manager here at Samtech, one of the co-hosts of Geek Speak. I am joined by my continual partner in crime, the one and only Scott McMurrow. Scott, how does life find you up in the beautiful state of Maine today?
Well, it's fantastic. We're at the end of leaf peeping season in the fall. It's a beautiful blue sky. The weather is nice in the high 50s, low 60s, and we're ready for a great Geek Speak today.
I am looking forward to spending some time with you and with our esteemed presenter. So to get us started, Scott, can you introduce our topic and our speaker, please?
All right, everybody. Well, today's topic is precision RF connector PCB launches for 224 gigabit per second devices, or how do you measure stuff and with low error and high bandwidth. And our presenter today is Sandeep, and I'm not even going to try to pronounce his last name. I'm terrible at that. Sandeep comes to us. He's been here for a little bit over a year at Samtech and has already, created a name for himself. His expertise is in RF connectors and RF and signal integrity applications of RF connectors, among other things. He's excellent at electromagnetics, and he's a principal engineer with Samtech. A little bit of housekeeping before we go forward. For those of you that have been here before and those new people, remember that we ask questions on the Q&A question and answer section of the page. In mine, it's down at the bottom. Don't use the chat window. It's kind of off and out of the way for us and gets in the way. I have some questions I may answer offline, direct to you. In other cases, we will stop the presentation generally at the end of a logical slide break, and we'll present the question to Sandeep. And remember that these presentations are available at Samtech Geek Speak about 2 days after the presentation. So usually by Monday, the presentation and the video is available. And then finally, I'm going to turn it over to Sandeep to go ahead and do what he does best and make this presentation. Thank you, everybody.
Thank you, Scott. So as the industry starts looking into 224 gigabit per second devices, one of the significant challenges is going to be how do you get the signals into and out of these devices with a good signal to noise ratio. That's especially true when you're trying to characterize these devices accurately. One way to do this is to use compression mount PCB connectors, because they can be placed close to the device, thus reducing the overall signal loss getting to the device. The compression mount, as the name suggests, is mounted to the PCB by means of pressure, either with screws or other mechanical means. They don't require any soldering. And it also does mean that they can be repositioned and moved around more than once. That being said, even using compression mount connectors mounted near the device, there are still significant challenges to be solved when we're talking about very high bandwidth devices. To understand that a little better, let's look at an example. Let's say you're trying to characterize the device shown on the PCB in the picture on the left over here, and you have a compression mount connector nearby. The equivalent cartoon schematic is shown on the right here, where you have the coax cable screwed onto the connector, certain length of trace going to the device at the other end. Ideally, you would want to measure the performance of the device right at these balls of the device, the connection to the PCB, but that's an area where complex electromagnetic interactions take place. And so we usually define the measurement reference plane about a half a millimeter or 1 millimeter away from this device, say around here. And at this point, the fields match the dominant mode of propagation of the signal, allowing us to de-embed to this point with accuracy. In most cases, the test instrument will be calibrated to the end of this connector over here, which means that when we are measuring the performance of this device, we still have the connector, its launch, and this section of trace to be de-embedded to see what the device actually performs like. To better understand what that means, let's look at the contributions of these various pieces in the path to the measurement. And here I'm plotting S parameter magnitude in dB on the y-axis versus frequency on the x-axis. The red curve on top corresponds to the insertion loss of S21, and that's really dominantly impacted by the trace and dielectric losses over here. The purple curve on the bottom here corresponds to the S11 or return loss seen at the connector side over here. And this is mostly impacted by the launch at the connector and the device itself. If we consider the connector, the launch, and the trace as part of the test fixture, and these S parameters actually are similar to the performance of your test fixture, there shouldn't be much of a problem de-embedding the test fixture performance from the overall measurement. In reality, though, getting this kind of performance is very hard. And if the launches are not properly designed, you'll see the return loss starting to go up at a much lower frequency. For example, in this chart over here, we see the return loss starting to climb past about 65 gigahertz and go steadily up. In fact, past 75 gigahertz or so, so much of the signal is being reflected back that very little of it is getting to the other side and it's starting to pull down the insertion loss as well. So the two curves start approaching each other. And from a point of view of measuring the device performance, a general rule to keep in mind is most de-embedding algorithms can perform de-embedding well as long as the separation between the insertion loss and return loss is at least 5 dB or better. This is not a hard and fast rule. This is more of a general guideline. Of course, in some cases, it does work even when there is no separation between them. But a general good rule to keep in mind is the 5 dB separation. So with that point in mind, in this example, even if your device performs great beyond 80 gigahertz or so, you're not going to be able to see its performance. In fact, for 224 gigabit per second devices, there is some talk about needing bandwidth in the 80 plus gigahertz range to truly accurately characterize the device. What that means then is we need to improve the launch design so that we can move the return loss from this red curve more to the blue or purple curve shown here. And that increases the separation between the insertion loss and return loss, thus pulling back the curtain on the performance of the device at higher frequencies. Hopefully that made sense on how a good launch design helps you a lot. Any questions so far? Okay. If that is the case, then I will move on to the next section where I will talk about the subcomponents of a wide bandwidth connector launch or any launch, so we can understand how to design a wide bandwidth launch. Most people, when they think of a launch, tend to think of the connector footprint, which comes with the connector data sheet. And this is an important document because it specifies all the mechanical features required to place the connector on the PCB and their sizes and things like that. But for any connector, the footprint will normally include a note that in effect says this is a generic footprint and it's not optimized for electrical performance. And that's because a true launch has many more features to it than just the footprint as shown by the picture here to the right. To explain each of the pieces you're seeing over here, let's start with the connector landing pad itself on the top layer, shown on the left here in dark brown. The minimum size of this landing pad is going to be governed by the size of the connector signal pin as well as mechanical tolerances. So it can't be reduced beyond a minimum size that will be specified in the connector specifications. And I'm also assuming here that we are launching the signal into the PCB, into a stripline layer. And to get a highest performance transition, it's a good idea to have the via in the pad of the signal branch rather than offset. And if you're going into the PCB to an internal trace, depending on the type of the via, if it's not a blind or a laser via or something like that, it's going to have a stub that sticks below the trace layer and impacts the performance. I will be sharing more details on what the effects of that stub is and how to compensate for it in a later section. But that's the signal via itself. The next part of the the connector launch is what I'm calling the inner ground ring. It's the set of ground vias closest to the signal, and they have a big impact on the impedance of the transition, as well as the frequency where the launch performance starts to break down. Again, more details I'll go into in subsequent slides. The next feature I'd like to highlight is what I'm calling the outer ground ring. And the main purpose of this outer ground ring is really to seal any gaps in the inner ground ring because manufacturing limitations won't allow you to move them all right next to each other. And this helps with things like crosstalk and providing good seal. The next feature to highlight is an impedance tuning feature. It essentially connects the pad of the via on the signal launch layer to the trace and helps manage the transition of the signal into the trace in a controlled manner. There are a few points to note about this transition, which I'll go over again in a later section. And the last main feature I'll highlight about the launch is the voids created in the planes around the signals. What I've tried to highlight by the red dashed lines on the right-hand part of the figure over here is that these plane voids are not going to be the same through the entire stack-up. The first couple of plane layers are actually going to be electromagnetically coupled to the connector body or pads or balls or whatever you have there. And so they will have a slightly larger size. As the via transits through the PCB, it's kind of a periodic dielectric plane, dielectric kind of structure. And so the openings will all have a similar size. If you have thicker ground and power planes in the middle of the PCB and you're traveling through that area, then the loading caused by the planes will increase because they're thicker. So again, the openings will be wider in that region. And finally, in the signal transition layer, the plane above and below it along with that transition will all have to be tuned together. And so there will be a different size there. So that gives you a rough idea of how each of the parts of the launch contribute to the overall performance. Any questions until here?
Not at this time.
Okay. In that case, I will move on to looking at 4 key areas for the remainder of the talk and how they impact the launch performance. The first area is the impact of via stubs. So of course, when I talk about via stubs, I am assuming that it's kind of a through-hole via, and the signal is traveling from the top layer of the PCB to one of the internal layers, not the bottom. So there is a residual stub in the via. The stub itself has a resonant frequency that is given approximately by this formula. Effectively, it's inversely proportional to the length of the stub and the dielectric constant of the via. While the resonant frequency is where a suckout happens and the impact of the stub is the worst, the capacitive loading provided by this via starts impacting this signal at much lower frequencies. So in reality, anytime you're talking about high-speed design or wide bandwidth design, these stubs need to be drilled away. And back drill is an operation performed by the PCB fabricators where they come back after the via is formed and drill away as much of the stub as they can. They can't drill it completely away because we don't want to take the risk of the connection between the via and the signal itself breaking, which will result in an open. So there is always going to be a residual stub length. And different manufacturers can hold tighter or looser stub lengths. For example, your fabricator might say that they can do an 8 mil plus or minus 4 mil. By no means am I saying that that is state of the art. Of course, you can get smaller stub lengths. That's entirely doable. But for the purpose of this discussion, let's assume that the stub has an 8 mil nominal length with a plus or minus 4 mil tolerance. What is the impact of that? To give you a feel for that, what I'm plotting on this graph is return loss magnitude in dB versus frequency for a single stub. And we've got 16 curves here with varying stub lengths from 0 mils at the bottom here in bright green, all the way to 15 mils at the top in dark red, and the other lengths in between. The point here is clearly you see the performance initially not get too much worse, but then get rapidly worse as the stub length increases. To visualize this better on this next graph, I've plotted the same data slightly differently. What I did was to pick the frequency at which each of these curves crosses the 15 dB return loss point. So on the larger graph over here, we have stub length along the x-axis and the crossing frequency along the y-axis. Now, 15 dB is still a good return loss. I'm not saying it's bad or anything, but it was a point to pick, and I chose 15 dB. And this black curve that I'm highlighting right now shows how the 15 dB frequency changes as the stub length increases. A couple of things to note here is initially when the stub length is less than 5 mil, the roll off in the frequency is not significant. even at 8 mil stub lengths, we are seeing only about 10% reduction. But you do reach a point where the curve starts rolling off quite significantly. And by the time we reach a 15 mil stub length, you've reduced that frequency by more than 50%. So it pays to really target as short of a stub length as you can. And it's unlikely that you're going to get really wide bandwidth performance if you start approaching, 8 or more mils kind of stub length as a rough guide. This is looking at the impact from a different perspective, which is in the time domain for those of you who are more familiar with that. This graph on the right shows the TDR of a single launch profile with 3 different stub lengths, 0, 8, and 15 mil. And you can clearly see that the 0 mil doesn't change the impedance too much. For an 8 mil stub, you get like a 10% impedance impact, while for a 15 mil, you get a 10 ohm impact. This actually not only affects the overall performance, but remember, we don't just have the launch on one side. We actually have the launch at the connector, and we have another stub at the device side too. So you really have 2 stubs that cause reflections between them. And so when you look at the combined performance of 2 via stubs with a short length of low loss trace in between them, the performance quickly gets a lot worse. So in the graph here, I've shown the return loss for 3 stub lengths, 0, 8, and 15 mils in 2 ways. The dashed line in each color is the performance of a single launch, while the solid line shows the return loss of the combination of 2 launches. And you can clearly see that the performance with 2 gets a lot worse, which makes your problem that much harder to solve. So again, the main takeaway, target as low of a stub length as possible. The other thing to keep in mind is the tolerance. So for argument's sake, let's say you have a 6 mil nominal stub with a plus or minus 4 mil tolerances. In some cases, customers have told me, well, if my worst case stub length is going to be 10 mils, let's just compensate the design around that 10 mil length and not have to worry about the others because they should be better. That is not true, actually, because I'm showing that in this slide over here, where I've tuned the design to minimize the impedance impact for a 10 mil stub length. But remember, 6 mils is the nominal stub length, which is already showing a little inductive behavior. And because the tolerance is 4 mils, you can end up with a 2 mil stub case, which is a lot more inductive because the design was compensated for the other end of the tolerance. And now you've got reflections because it was designed around the wrong point. There's a wrong design point. So it is best to design around the nominal case and minimize the tolerance, because the tolerance number need not be repeatable at every via location. So you can have a longer stub on one side of the channel and a shorter stub on the other, and cause problems because of that too. So the main takeaways from this section are that it is extremely important, if you're not using laser or blind vias, to get as short of a stub length as possible, and to also design around the nominal stub length and keep the stub tolerances as low as possible to get a better overall design. Any questions at this point?
No questions, but I'll just make a comment. If you could just move back one slide.
Please.
And so this is a really important takeaway that we optimize our vias with a phenomenal stub length. And the problem with either inductive is what we want is we would like in the time domain all of the reflections to come off of a low impedance, a lower end, either no impedance dip there or a low impedance dip. If you have this case where in some cases you're a low impedance dip, and in other cases where you're a high impedance bump, that actually changes the reflection coefficient at that point in the interconnect. And what that does is it causes an inflection point in the return loss curve that kind of, you'll see the behavior actually flip at that point where it goes from capacitive to inductance. And so it makes it much harder to predict what's going to happen in a real system because these things all basically add up in a very strange way as the waves reflect back and forth. So it's very, very important for us to get the nominal dialed in correctly so that we have much less variation with respect to the nominal impedance. Thanks.
Thank you, Scott. The next area that I'm going to focus on is the sizing of the ground ring. So as I mentioned briefly previously, the inner ground ring controls the impedance seen by the signal as it travels down the via, as well as the point where the launch starts, the frequency at which the launch starts breaking down. And a rough way to start sizing this ground ring is to treat it like a coax. Use the coax formula as shown on the right over here and use the shield diameter of the coax to be the ground ring diameter and the signal diameter as the signal diameter of the coax, and size things that way. Keep in mind though that this is only a very rough, crude approximation. In reality, the signal traveling down the via, it's seeing more of a periodically loaded transmission line. The only truly coaxial aperture is where the plane crossings are. And if you look at the launch with a high enough bandwidth, you will see a periodic structure where you have the plane, then you have the dielectric space, then another plane, and so on. So this is just a starting point, and you will need to tune this better in simulation. Also remember, previously I mentioned that the plane cavities, their size changes along the length of the via depending on the area of the cross-section they are in. So all that to say, this is just a rough starting point to start your design process, not a hard and fast rule. Another thing I want to highlight is this relative dielectric constant seen by the via. What do I mean by seen by the via? This is especially important as we start designing high bandwidth launches. The signal does not see the same dielectric constant while it's traveling down the via as it is when it's traveling down the trace. And the reason for that is PCB structures are laminates. They consist of resin and filler. So in this picture, for example, I'm showing a PCB cross-section with planes, glass fiber, and resin. As the signal is traveling down the via, it's from a dielectric constant perspective, it's seeing alternate glass, resin, and so on, which is going to provide the dielectric constant it's seeing. When it's traveling down the trace on the other side, depending on the type of glass cloth, how close the glass bundles are, how spread out they are, things like that, the overall dielectric constant it sees are going to be different. For the design of a wide bandwidth launch, what we really want to target is materials where, or PCB laminates where the glass and dielectric and resin have dielectric as close to each other as we can get, along with the low loss tangent and dielectric overall dielectric constant that's as low as possible, because that helps push the bandwidth to a higher frequency. Why? Because every structure can, beyond a certain frequency, support additional higher order signal transmission modes. When we are talking about connector launches and things like that, what we are really focused on is the fundamental TEM mode, which exists from DC onward. But above a certain frequency, higher order modes can propagate down the same structure. And when that happens, it takes energy away from the fundamental mode and causes all kinds of complications to start happening to your performance. So we really want to stay below the cutoff frequency for these higher order modes. A formula to give you a sense of where that occurs is shown on the right. The main takeaway is it's inversely proportional again to the dielectric constant seen by the via, as well as the size of the ring. Hence the importance on getting the dielectric constant as low as possible. To give you a sense in terms of what type of numbers we're talking about, I am showing a chart here where I've plotted relative dielectric constant along the x-axis and drill diameter along the y-axis, because a smaller drill diameter allows the ground ring to come closer together, hence pushing out the cutoff frequency. The numbers in the middle all indicate the cutoff frequency in gigahertz based on drill diameter and relative dielectric constant. What's the takeaway here? If you're trying to target 224 gigabit devices with 80 gigahertz plus bandwidths, you really want to use drill diameters that are 5 mils or lower, and dielectric constants in the 3 or even lower range if you can. So this kind of gives you a quantitative feel of the cutoff frequency. How does it show up on the performance curve? For that, I've plotted an S parameter magnitude graph over here. The calculated cutoff frequency point for the structure is around 85, 87 gigahertz or so. And you see the return loss starting to climb and the insertion loss starting to roll down, effectively limiting your de-embedding band. So that's the importance of having a really high cutoff in the design of the launch. This gives you a quantitative feel, but to help you better understand what's going on, let me show this chart over here, where on the left, I'm showing a signal via going into the PCB along with the trace on the left, surrounded by ground vias around the signal launch, which are shown around it. In green is the section of the via going into the strip line, which is where we want the signal to flow. But remember, this PCB structure has planes and other things in it below this. So you have a bunch of rectangular cavities formed by all the plane cavities, as well as a circular waveguide formed by the region of the via below the launch layer. So if I look at this structure from the side, this is the signal via. I'm showing it in cross section. So you're seeing one ground via right behind it and all the plane layers. And let's look at how the field flows down the structure, both below and above cutoff. On the left over here, you have the signal going down the strip line. There's very little of it going into the plane cavities and things like that. That is how we would like the signal to flow. Above cutoff, though, you see a significant proportion of the energy flowing down the plane cavities, and that energy, of course, can go to other parts of the board, cause emissions, crosstalk, other things. Basically, that energy is not flowing down the strip line where you want it to go. These are just pictures, but there is an animation of this for you to get a better sense, which you can go to the link provided here at the bottom and view. So while these field animation make for very pretty pictures and help you understand what's going on, they do take a while to compute and are computationally intensive if you want to do a bunch of them. It would be good to have an easier way to visualize at which point your launch breaks down. And that does exist. It's a metric called loss factor. The loss factor equation for a two-port structure is shown in the middle over here. What this is basically saying is the loss factor is a measure of the amount of power that is not either transmitted or reflected back. Basically, it's lost in the rest of the structure. It's going somewhere else. So this metric allows you to see if indeed the structure is breaking down when you plot it. So if you look at the graph over here, I've plotted the loss factor versus frequency for the structure I showed the field plots previously. And at lower frequency, you see the graph climbed up slowly as the trace loss and dielectric loss increase. But at a certain point, you see the loss factor increase significantly, and that tells you that the launch is breaking down at this point. Now, in this case, I did not remove the metal and dielectric losses. This change in slope will be even clearer if you simulate the structure with perfect metal and lossless dielectric. It just will make it a lot clearer. So to summarize this section to this point, a smaller drill diameter and a lower dielectric constant material will allow you to push the bandwidth of a launch to a higher frequency, and plotting loss factor is a means of seeing where the launch breaks down. I briefly skimmed these topics. A lot more detail can be seen in a presentation given by one of my colleagues at DesignCon this year that I've given the title of on this slide. Any questions on this section?
Here's one question. What is the impact of the ground via diameter on F cutoff?
So as the ground via diameter increases, the pad size of the ground increases. That means the grounds have to be moved farther away. That will affect where the launch starts to break down. That's a very simplistic way of starting to think about it. Of course, solving it in a field solver will give you a deeper appreciation of the nuances.
Yeah, that's a very good description, and I'll point out usually the limit is the manufacturing tolerances, right? The smaller the ring we can get, the higher the cutoff, the higher the bandwidth, and generally we never run into the point where the vias themselves, the barrels, without the pad loading, turn capacitive. They're usually high impedance, and we load them down with the pads and the planes. But it's the manufacturing tolerances that keep us from bringing that in closer and closer.
Exactly. Yeah. Thank you, Scott.
Thanks.
The next focus area is misregistration compensation. So I think everybody understands that when a PCB is manufactured, everything is not going to land up perfectly where it's designed. So misregistration is where the features on the different layers don't line up exactly as they're supposed to. So in the picture on the right here, I'm showing the X-ray of one of the test boards that was built at Samtec, and you see that this is a via going from the top layer to layer 2, and the pad on layer 2 is offset from where it's supposed to be more than what was expected, and the blue arrow here indicates the direction of the misregistration. But what does this mean for the signal? To understand that better, let's look at this chart. There's a lot going on here, so let me take a minute to explain what you're seeing. At the bottom here is a photograph of the test board. It's showing two differential traces coming out to connectors at each end. And on the right-hand side is an X-ray image showing 4 of the launches on the board. The red arrow over here highlights the direction of misregistration, which on the photograph is the same at all the connector launches. That is the direction of misregistration. The traces, on the other hand, exit at 45 degrees to come together to form the differential pair, and then at the other side separate out at 45 degrees to go to the connector on the other side. So depending on the connector location, the blue arrows indicate which direction the trace is exiting on. What we see is, depending on the direction of the misregistration and whether the traces are exiting parallel to that misregistration direction or perpendicular to it, when the misregistration happens, it has a big impact on the impedance that is seen. Why is that? So let's look at let me go back to this picture for a second so you can see clear. Here, this impedance transition feature has a rather rapid change where the antipad is for the via. When you have a rapid change in dimension, any small shift in the antipad due to misregistration or even the other features is going to cause a big impedance change, because these are all tuned together. So moving one of these features is naturally going to affect impedance. Now, when the misregistration happens parallel to the trace launch, the abrupt change in dimension has a much greater impact, because now you either have a narrow trace over a void or a wide trace over a plane. When it happens perpendicular to the misregistration direction, the impact on the impedance is a lot smaller. So this is shown very clearly when you overlay a bunch of these measured traces on top of each other, and you see this significant variation in the impedance when the trace exists parallel to the misregistration direction, whereas the variation is a lot smaller when it's perpendicular. Now, to a certain extent, if everything is consistently off in the same way, you can compensate for it to a certain extent. But when things are varying a lot, there's really nothing you can do, and it is going to show up in the measured performance. There's not a good, clean way of de-embedding it. So when you are designing the PCB launch, it is really important to pay attention to the tuning done at the transition from the via to the trace. A good recommendation is to avoid structures that change their dimension abruptly near the antipad transition region. Consider more of a tapered or even Scott suggests using an exponentially tapered launch, for example, with the end of the taper transition happening about 0.1 millimeter past the antipad start. Because the advantage of an exponential taper is the change in dimension happens a lot at the beginning, where even if there is misregistration, it's not going to impact the impedance too much. And the changes are much slower in the area where the antipad edge is. The other thing to do is when you're designing diff pairs, don't exit at 45 degrees to bring the traces together very quickly. It's better to bring out the traces all in the same direction. This is especially the case when you're talking about multi port connectors like a Samtec bullseye and things like that. Bring all the traces out in the same direction, and once you're past the antipad region and things like that, bring the traces together. This way, even if there is any kind of impedance offset, at least it's consistent for all the launches, and you can try and compensate them to a certain extent. So to summarize the takeaways from this section, the taper transition is a good way to minimize the impact of misregistration, and keeping the trace escape for all the launches the same way also helps with making the design more robust from a manufacturing perspective. Again, I skimmed through a quite detailed section. You can get much more details in a presentation a colleague of mine, Gustavo Blondo, gave at TDICon in 2018, and the paper is cited here at the bottom. Any questions on this section?
No, we're good.
Excellent. The last area that I want to focus on today is dealing with variations caused by connector assembly. So when we mount compression mount connectors on the board, we usually place them on the pad and put screws through the screw holes of the connector to compress them onto the board. While you're doing this, you have to hold the connector fixed, and sometimes as you're torquing the screws down at the very end, if you're not careful, these things can rotate slightly. Because we're talking about very high bandwidth connectors, all the feature sizes are small, which means any slight offset can produce things like here I'm showing a microstrip where the doghouse opening of the connector is now come really close to the trace rather than being symmetrically positioned as shown on the right hand side. And this again shows up quite clearly in the performance. Here I'm showing a TDR with a 90 gigahertz bandwidth, where you can see the connector that was misaligned causing quite a significant capacitive dip where the doghouse comes close to the trace. Keep in mind that at least when we're talking about surface traces and connectors for surface traces, you can at least see the doghouse. If you're talking about a strip line, you won't be able to really see the pad visually, and you're kind of doing it somewhat blind. So one way that we have figured out that works quite well is to work with our PCB manufacturer to specify really tight hole sizes and tolerances for the screw holes. That way there isn't much slop to begin with. Another thing that worked really well is to drill the screw holes in a secondary operation after the outer layer pads have been completed. Use an optical tool to visually align to the actual pad location and then drill the screw holes. This does introduce an extra step, but by doing that and specifying a datums with tight tolerances to constrain the position of the mounting hole, we've been able to assemble the connectors blind in many cases without having to readjust it and get a good location of the connector on the launch itself. A second thing you can do is to choose connectors that have notches in them. Here, for example, I'm showing a Samtec 1.35 millimeter connector with notches in the body that you can then use to compare to features that are etched on the PCB itself. So when you place the connector on the PCB, they align with those marks on the PCB and provide you a nice visual guide or visual confirmation on whether the connector is placed properly or not. This can save a lot of time and frustration when you're trying to debug a problem. At least you don't have to wonder whether you placed the connector properly on the board or not. That covers all the focus areas. In conclusion, the key takeaways to take from this Geek Speak are: the launch is much more than just a mechanical footprint. It does require care and design and simulation. Don't just assume that because a launch worked on a previous design with a similar stack up, it's going to work on the new design with a higher bandwidth and things like that. You really have to go through the design process and verify that. Choosing PCB shafts that can do smaller drill sizes and tighter design rules will allow you to push the cutoff frequency of the launch to higher frequencies. If you are going to use through-hole vias, please work with your vendors to get the shortest possible via stubs with tight impedance controls. Also, when transitioning from the via to the trace, consider using an exponentially tapered or tapered transition with as minimal change in dimension as possible within a plus or minus 0.1 millimeter distance of the antipad boundary. And finally, use copper features and tighter positional tolerances in the screw hole locations to minimize assembly variations when mounting the connector to the PCB. That's everything I had to cover. I'd be happy to answer any questions or entertain any comments.
Well, I have a couple of comments. Can you flip back to the slide that shows the TDR, the connector, just a few slides back? There we go. So for blind, essentially blind mate connector, which is what a compression connector is going into a via in strip line, even the best alignment techniques that you can use, you can still be off. So what I would recommend is to finalize in the laboratory, either using a TDR or probably better yet a VNA with a TDR output that can be turned into live kind of repeat mode. What you can do is use that to TDR or basically VNA or TDR multiple launches simultaneously. If you've got 4 launches, well, you can do that with a 4-port VNA. With a TDR, you only get 2 ports. But basically what we care about in de-embedding is that the launches are as identical as possible. So if you loosen them to the point where they're a friction fit, you can then take the launch and gently nudge it while you're making the measurements until you get it to pop in so that they're as identical as possible. And that's an old technique I used many years ago to align connectors, and it worked well then and now. If you don't do that, any error that you have here is error in the embedding that you can't recover from. There's no way to fix. You can't fix it because it's part. The de-embedding process assumes identicality of the launches. So that's kind of the last trick that I would say is you can do this live with a TDR or a VNA. Generally, we use a VNA because they're less sensitive to electrostatic discharge. It's possible to move a connector or pin around on a test board and accidentally induce charge that blows out the TDR head. So there you go. Any other final comments, Sandeep?
No, sir. I'm good.
Everybody, I hope you enjoyed the presentation. There is, oh gosh, a good 15 to 20 years of experience involved in what was presented here. It's been boiled down into things that are fairly simple. I hope you appreciate it and hope it helps your next designs. Any final comments, Matt?
We just continue to thank our attendees for supporting GeekSpeak. We thank Scott and Sandeep, especially Sandeep, for doing all the heavy lifting today. One of our questions we always get is, are our GeekSpeak presentations and recordings available online? The answer is yes. Within 24 hours or so, we'll have the recording and the presentation available at geekspeak@samtech.com. Please contact the GeekSpeak team at geekspeak@samtech.com with any questions. And if you have anything specific SI related, you can reach out to our SI leaders like Sandeep and Scott at sig@samtech.com. With that, we wish everybody a good day, and we'll look forward to seeing everybody at our last GeekSpeak of 2022 in December. Check out samtech.com/geekspeak for more details for title, presenter, and registration. With that, we'll wish everybody a great day. Thanks again, everybody.